let's start again. Welcome back to our seminar, and our speaker today will be our own organizer, Hong Van Le. She will talk about work that just recently got put on the archive. It's about CR-twistor spaces over manifolds with G2 and spin 7 structures. So please go ahead.
Yes, thank Igor. Thanks for providing me the opportunity to talk today, because of that, suppose that you talk, right? So I say that very luckily that we just got the new reason is Domenico Fiorenza, and he put on the archive last week. So I should talk about CR-twistor space over manifold with a G2 and spin 7 structure. So the plan of my talk is the following. First, of course, I have to say about motivation. Why you want to work, and why we think that you want to listen to this talk. Yeah, and then I should describe the main reason. That is consists of the construction and the formal integrability of the CR, that means Cauchy-Riemann structure. And then the later part, I outline some the main idea of the proof of the theorem. And the last part may be the most interesting for you. That is the open problem, which I think that could be interesting for you. Okay, so the motivation and the prior work, that means that's how to say G2 and spin 7 structure is nowadays considered one of the fashionable topic in geometry and theoretical physics, because that and theory. And the G2 and spin 7 structures that they have also interesting for people working in algebra, because there are a lot of the symmetry related to Octonian, and some my friend who working on the symplectic geometry, he says that's too much symmetry. That's hard for people who know only symplectic group. But I check also got some request from the Pasha Zuzmanovic. That's his student Czech wrote a thesis on the Octonian algebra. So I understand. We should have so many people talking about G2 and spin 7, and only the symmetry are related to Octonian algebra. So that is why that's interesting. And then, okay, so who the Czech want to say that's one of the very famous mathematician working on G2 spin 7 structure is Robert Bryan. He wrote in his preprint in 2005. That's for him. That's he wrote a book on the, how to say, differential form system of the PD. For him, that's is a more easy and convenient to work at G2 and the spin 7 structure as a differential form, because you can manipulate them very easily. But from my point of view, that is there are many, how to say, parallel form like a G2 and spin 7, so that we will only manipulate it's a differential form. You don't understand on the symmetry generated. It's a Octonian, and that's why we are want to use a vector cross product. That is a kind of higher symmetry structure than just using differential form and the Lie group. So that's a great. He introduced the notion of the VCP structure. He thinks that a generalization of the almost complex structure. Yeah. So what is a VCP structures in terms of the gray? That is a mapping from the stereo algebra of degree R. If R equal 1, that is a Czech linear operator V to V. And satisfies that the following properties. That's the image of the Z1 of the V1 VH VR is a perpendicular to the plane spanning by V1 V to VR. Yeah. So you have the map, the plan, because the element, of course, has not clearly planned, but I mean that we consider decomposition, decomposable vectors, and is can associated some are plane. Yeah. And you extend it linearly. Then on these things that's a map to the park is a perpendicular to that R plane. And then it's should also preserve, how to say, metric naturally defined on the V. And then now, of course, that's now that you can make pleasure for Robert Plan, say that for this VCP form, you associated another differential form by taking scalar product. Okay, so that is a gray and brown classifies that's a zero R-form VCP structure exists on Rn if and only if is a R equal 1 and the n even, that is a almost complex structure, a complex structure that we know R equal n minus 1, that means one dimension lower, and then that is a two, how to say, exceptional case, that means R equal 2 and n equal 7 and R equal 3 and n equal 8. So the case that is n minus 1 phone VCP product on Rn is defined uniquely by an orientation on Rn. So that is a thing. And then, but that's a much interesting for us. That's the case that's Rn equal 2 and 7. And in this case, the associated form, 3 form is the associate 3 form. We stabilize is G2. And if Rn equals 3 and A, then that you have the 4 form Kele, and stabilizer is in 7, is in SO8. So as I already said, that's a great introduce the notion of VCP structure at generalization of complex structure. But now it thinks that a CR, Cauchy-Riemann structure, can be also considered at generalization of the almost complex structure. And that is related how to G2 and spin 7 that I should talk about now. But first, that in the already long time ago, that 1984, LeBron constructed a CR-twistor space over any conformal manifold, and proves the Forman integrability of the CR structure. Yeah. So that's the next year, this construction has been generalized by Rossi, and then he also proves the Forman integrability of the CR structure. And then only, how to say, long time, more than 20 years later, right? The Verbitsky generalized the Lebrun construction of this star space to the case that is R equal 2 and M equal 7, and the proof that the CR structure is integrable or Forman integrable, because the pupil use the Forman integrability and integrability interchangeable. But his proof is not correct. Last summer we exchange sent some email to him. He didn't reply. Okay. So now let me start the construction of the CR-twistor space and discuss about the Forman integrability. So assume that's a Riemannian manifold and G symmetric is an unoriented Riemannian manifold. So I denote by GR plus and subscribe R minus 1 and the Grassmannian bundle of the decomposable units R minus vector in the exterior product of the tangent bundle. So that's a notation. Here's a little bit different from the what we wrote in our archive paper. The problem because in this how to say transparency, I have much less place. So to put everything in to be displayed, I have to change the notation a bit. But that is the only thing. So I denote by the P, that's a natural projection. Yeah. So now for any unit oriented decomposable R-1 vector, I access the plane, oriented plane. Yeah. So I denote it by EV. So that is associated to it. And I denote it EV orthogonal, the orthogonal complement of that EV in the tangent space of the M as the point projection of the point V. So now you know that on the tangent vector bundle we have the Cauchy-Civita connection, and then because that connection induced trivially on the connection of the R-1 exterior product of Tn, and I denote by the same, that's a Cauchy-Civita connection. And then this once you have the connection on the vector bundle, then you can talk about the horizontal space. And then because this guy is inside on this vector tangent bundle, so therefore I can decompose the tangent bundle as a point of V of Grassmann bundle as a vertical component that is lying in the inside the exterior product of the R-1 of Tn. And the plus is a horizontal vector space, and the horizontal vector space at any point is the same, that has the dimension as the dimension of the manifold on the base. So that's and that is a horizontal. You have the, how to say, isomorphism, and the vertical is like that. Now for manifold and I fix oriented Riemann manifold. I let me be the rank n minus r plus 1 distribution on the Grassmannian bundle defined by the following inequality. That means that that B is on the horizontal subspace, and then that is it's therefore it has a isomorphism to the tangent space on M, and I take the BV is a set up on the VW, such a projection is belong to the perpendicular to the V. Yeah. Okay. So now that's if I have the R-form structure on energy, then the small lemma, that is a EV perpendicular, have the complex structure by the chi. That chi is the vector product V times ZW. That is actually that Z is how to say, you can think the following, the almost complex structure on the big space, and if you induce R-form VCP structure on the big space and induce the VCP structure on the this bond space, because of dimensions, that VCP structure is a 1, because it takes the dimension 1, so therefore such a complex structure. And that is a lemma, it's hidden in some general theorem in the gray paper, and it was emphasized the paper by Leung, and then in our paper it's Domenico. We use it for study of the Forman integrability of complex structure on loop space. So it thinks that Yes, sometimes some statement you have make very clearly. That is how to say it was hidden in some previous paper. So that is induce a complex structure on BV and it's defined by the following question. Yeah. So that I noticed that GAV is defined on the base space on G Chi is on the B. So it's the kind of the commuting like that. So an almost CR structure on manifold N. Now that's a general definition. That is the definition for the case of the manifold VCP structure. But the definition of almost CR structure on a manifold N is a pair of the some distribution B on the tangent space of manifold N. And GB is a almost complex structure. That means personally defined. If GB B equals the whole tangent space, and you have the almost complex structure. Yeah, so that is a generalization of almost complex structure. So the almost complex structure is called formal integrable. If you have the similar in the case of the complex structure, but some people say that integrable, but we don't have the Martin theorem. Yeah, so I mean that's therefore, you don't know that means that formal integrable is what is integrable. Yeah. So I stick to the notion of formal integrability. That several people also use the same like that. So if B and G is a formally integrable, then the type of the N B JB is called CR manifold. So now let us make some equivalent formulation for the case in our case. That means you have the Grassmannian bundle with a distribution on the horizontal space, yeah, and then define Shibai by restriction of the VCP product on that orthogonal complement. So now we define the equivalent formulation from the of these things. That's the first. That's for any x, y. It's a vector field. It's the value in B. Yeah, I take only vector field of the value in B on the Grassmannian, and then you have the Lie bracket of GB and XGB of Y. Yeah, that is a GB is our case. That nothing as a G and the chi. I write that minus xy is in gamma B, and for any xy in gamma B, you have the second thing, that's a projection of the guy, and that's the more or less the same thing like that, because but I have GB in left hand side and right hand side, by therefore here is plus and not minus. Yeah, and then you take the projection on B, then therefore you can apply GB, then it equals 0. So it's a little bit more complicated than if you see in the case of the Nijenhui tensor in for almost complex structure. So what is why you came to this condition? In fact, that's in literature, people only have some similar thing like that, but not exactly. That's first they also have let us see. The first condition is you see does not you can rise for any, how to say, on CR structure, yes, as GB minus GB in XY in gamma B. But for the second condition, you need projection to B. That means you need to some splitting, right? And that is at the moment it can be done because we have splitting of the Grassmannian into vertical and horizontal. So that's therefore that's in the literature they don't have considered such splitting. And they replace the condition 2 by another condition like that. And if you look at the condition, of course, it had meaning only the first condition hold, because otherwise how you can apply Shibai to that second component. And then so he modifies the condition, adapt to our case, and you call the first condition is the first integrability condition, and the condition 2 is a second integrability condition. Now that's it gives the following definition. That's let and machine be endo is the VCP structure guy. The almost CR manifold that is a oriented Grassmannian bundle of R-1 plane or that distribution B is the horizontal, yeah, that perpendicular to V, and the is that complex structure J defined on that B is a CR-twistor space over a Riemann manifold in those is the VCP structure guy. Now example. The first case is that of course that you consider the I'm sorry that here yeah so yeah that is a on-phone VCP product on the Riemannian manifold of dimension and 2n that is a Hermitian manifold, yeah, Hermitian almost complex structure. So in this case that you have the GR of the R-1 is 0 is nothing as a M2n. And the horizontal distribution is the same tangent bundle. You don't have the vertical. And the almost complex structure of the G is identifies the almost complex structure on M. So the second case that means that the Rossi case that covers the case of LeBron. That means that you have the n-1 phone VCP product on an oriented manifold. Then the distribution B on these of the Grassmannian bundle of n-2 m is two-dimensional, and the CR-twistor structure it coincided is the one that constructed by LeBron and extended by Rossi in 84 and 85 respectively. And you know that if you consider complex structure in dimension 2, that is quite easy, mostly that everything is integrable. Yeah. So the case that non-trivial, of course, to figure out some construction is one thing, but then you have to prove that is another thing. So that's a much interesting. The next non-trivial case is a two-phone VCP product on the 7-dimensional manifold, Riemannian manifold. Then the CR-twistor structure on the Grassmannian bundle of the 1 and the 7, and that is nothing else as sphere bundle. Yeah, sphere bundle. A coincide is the one constructed by Verbitsky. So the sphere bundle is something also more how to say, classical one, and then now I didn't write that is it. Example. Okay. So that's the last case. That means the 3-phone VCP product is had been constructed in the paper by Domenico and myself. So now the example implies that the M2 energy in the is the one phone VCP's product is a CR manifold if and only if the almost complex structure is integrable or the same like a Forman integrable. And then I only say that because it's a LeBron and Rossi case, the structure is two-dimensional, and that they also prove that on CR manifold the structure is integrable. And Verbitsky shows us the CR-twistor space provided the two-phone VCP structure is a CR manifold if and only if C is parallel. And unfortunately, his proof is a wrong argument, and we spend a lot with the Domenico many, how to say, days try to understand his proof. Yeah. Then he find some how to say, where place argument breakdown. if that's the case, then you can use it to study holonomy G2 manifold, and really that's why nobody use it. Okay, so of course, integrable CR manifold has a trivial case that the CR-twistor space over any flat Riemannian manifold in the is a parallel VCP structure is CR manifold because everything is parallel. So now is our main theorem. We proved really that is a finished proof only this year before we put it in archive. So let GR -1 plus, that means that's Grassmannian of the oriented R-1 plane over manifold with the VCP structure. Yeah, so let here the CR-twistor space. Then there exists a tensor. That means what is tensor? That's a section of the bundle over Grassmannian, and this bundle is a bundle of the two form. B star is a dual space. So two lambda 2 B star, that means two form over B, and the tensor is the PGR plus 1 n. That means that's a taking value in the tangent bundle. So that means that this tensor is you can consider as a two form over anything on B, and it's a tangent value bundle. So that's the success. The first CR integrability condition holds if and only if for any V in that Grassmannian bundle, we have such the vertical component of the TV xy equal 0 for any xy e in the BV. So that's because that is you know that's I say that's it take value in tangent bundle and tangent bundle of Grassmannian because it has the natural connection. It decomposes on the horizontal space and vertical space, and the TV of 6 that means that's a vertical component of that tensor taking value at any x and y only vanished. So then now we look at the first integrability condition for the case Rn -1 equal 1 and 2 n. Then we see easily that we check online argument that the vertical component is ongoing equal 0, and it's the same thing also take maybe that a bit a two line of argument. Then you got that if the case of the LeBron and Rossi considers and vertical component is only equal 0. And then now let us consider the more interesting cases that Rm equal to 7. Then the vertical component equal 0 if and only if the main underlying manifold has constant curvature. The same thing for the case of the Rm equal 3. 7, that means G2 space 7 manifold. Then the vertical component of the torsion tensor vanished if and only if the underlying Riemannian manifold has constant curvature. So that is we solve the question on the vanishing of the vertical component. Now the second CR integrability condition hold if and only if for any V in the GR plus n and x plus y, you have the horizontal component of xy equal 0. So now let us try to apply this reason to the case that is a more or less easy case. That means that's a one-fold vector cross product. Then it says that the horizontal component is vanished if and only is of course that's a chi is integrable. And then you can also check very easily that in the case of LeBron and Rossi, then horizontal component only equals 0. So now the most interesting case that is the G2 and spin 7. Then the horizontal component equals 0 if and only if you have some linear combination of some how to say covariant derivative of the associated VCP form equals 0. So covariant derivative of this form, yeah. So you take the linear combination. Actually, if you thinking of what is the high integration, yes, that is a Gray and Henrika also write the condition by write some linear combination of some covariant derivative of the associated form equals 0. So that is you can think that's a little bit analog of the Gray and Henrika, but they didn't need yeah. So that's of course that's if nabla of the associated VCP form equals 0, then everything equals 0, and the nabla of the VCP form is equals 0, and if and the only if that chi is a parallel. And therefore, if chi is a parallel, the everything is a how to say vanished. But you have not checked that if there are some non-trivial case or not, possibly have, yeah. But I think that's but of course I think that we have some example, but I'm not sure because the computation sometimes very long, yes, and you may make some mistake. But much interesting that's the case, that's a parallels and everything vanish. So how to prove it? So so that's for the proof of the main theorem. We need to understand the first that's a not very vertical component, but the xy, the I did notice that is the let me show that the thing is the following thing. So you have the you can consider here that is a V is a EV that you can think that is equal B, and now it takes everything here is in horizontal. And then you have the vertical space, that's T vertical, and here's the horizontal. So you have a vector decomposition, first at vertical and horizontal, then I have decomposition like that. But for the computing definition of the CR integrability, you need to decomposition in terms of the projection over B and the anything answer. So that means that you have another decomposition of the tangent space that B plus AV plus T vertical. And then for understanding the first integrability, you need the xy Lie bracket, and I denoted the perpendicular to B. That means I need to consider this part. So T vertical plus AV. Yeah. So then that is since after several, how to say, base of the lemma, it concludes this part. So you can ignore. Yeah, that does not contribute to the xy. So that is that lemma. Xy Lie bracket is belong to B plus the vertical. So you don't have the EV here after taking the Lie bracket. And then now once you have it, then you use the theory of the affine connection is say that the vertical component is a tensor. And then taking into account the lemma 1, you get the it seems that I don't have okay. Text says then I have the following result. That means the vertical component equals 0 if and only if that is a Lie bracket of gx and Lie bracket jy minus xy belong to B. And that is a first integrability condition in our paper, as well that's also in many people. Yeah, that is first integrability condition. So this proves the first accession in the main theorem. To prove the next part of the theorem 2 and 5, then you need to express vertical component in terms of the curvature tensor. And now, of course, the curvature tensor, you have so many ways to write it. People sometimes like a curvature tensor is like S being a square of the lambda of T n. But because SCO T n G is how to say, using Riemann metric is also identified. It is a exterior of the Tn, but that is more interesting to use this expression. That is a not this expression that in many has a classical book on differential geometry, but it uses this expression. And then it has the following proposition. The following are equivalent. First, for any V in the Grassmannian plus R minus 1n, you have vertical component equal 0. So that is what you want to have. Now you try to see that, what is the real condition. And second condition, that's for any V in R error plus 1n, and for any V3 in the perpendicular space AV, and any V4 in the AV, the orthogonal projection of the SO AV. So what's the orthogonal section? Everything is a subspace in the Lie algebra SON. Yeah, that's a SOTN of G. And AV is a subspace in TV. And then you use a Killing metric, and you take the projection on the Lie sub-algebra. And the projection on Lie algebra is lying in the unitary algebra of G and GV. So you can write equivalently, that's a Lie bracket of the operator of J, and the projection of it equals 0 at element in SOAV. Yeah. So so that means that's use this proposition 1 and 2, then it's you can prove main theorem for the case R and equal unfold vector cross product, or R n equal n minus 1 n. That means that's a Leblanc and Rossi case. So that the theorem follows easily from our proposition. And then that's because how to say. But the most interesting case that is T2 and spin 7, because you see there are a lot of non-trivial equations that actually that infinitely many equations. And then vertical equation if and only if the tensor of the curvature of the Riemann manifold satisfies an infinite system of the linear equation. So how to write it? So first given a V and a G, that means a VCP product, and V is a Grassmann abundant of the two vectors, because you see that's a curvature taking value on this Grassmannian, right? And that you need only to know this value, anything else expand by linear. So that's a review, but that on the tensor in SCOV, suggest projection of CORV perpendicular to RV is a commute is a GAV. Yeah. So that's this space. I mean that's you compute that for the case 3n. That is non-trivial. That is how to say. For dimension, for example, 3 and 7 case, this space have dimension 10. That is a non-trivial subspace. So the following lemma is immediate from the definition of the subspace RV and the proposition 1. Lemma 2. The first condition of Forman integrability of CR-twistor space holds if and only if for any V in Grassman 2V, the R is a vector of the two form is a value in Lie algebra. And if it takes a value algebra, you compute it, then it's a RV is the sum subspace in the Lie algebra, right? And then that is a how to say infinitely many equation. So of course that's the overdetermined system equation. And then first it says that how to solve this overdetermined system of equation. Then poorly problem of Lie algebra. So now it denoted RCV is the vector space of the algebraic curvature that is satisfies the following algebraic identities. That it's a no that's from the Kobayashi no Mizu that is in catalytic design on the algebraic curvature. And then it denoted CR-V chi, the subspace of those elements and satisfies this the equation I showed in the previous slide. CR that Cauchy-Riemann, yeah. So we ask what is the solution? This how big is this solution space? Now that's first we make some observations. That's any how to say algebraic curvature of constant curvature, section curvature is solution. Yeah, that linear system. So therefore, you can multiply with any lambda. And then now to prove the main theorem, that means that's a case that we claim that for G2 manifold, you have only constant curvature. How to prove it? First, it spend a lot of the which, yeah, there are different proof. And then it takes us we don't want to compute so much. So then, how to say? Then he says that why not to ask the computer do the job for us? You have to only to write the code for the program, yeah. And the code is written in the appendix. It took about less than 4 pages. It's a command on the command. I mean that's a. Then he run it. Then first he run on some very old computer. It ran 10 hours. Then Domenico says that let us try to some more modern computers that only not so modern. That means that usual today 2 gigabyte, 2 gigahertz, and the core, and it takes only 50 minutes. So that's that for the G2 case we do for computer. Now for the spin 7 case, of course you also have the computer proof. It took us on the same computer where it ran 50 minutes for G2 case. Now it took almost 11 hours for spin 7 case. But we have quite a short proof, theoretically, less about 3 pages for a spin 7 case. So that's how to do it. That first you make the reduction argument that actually you notice that the condition satisfies of spin 7 case is a bigger space and there are more equations. More equations, then it try to restriction and by projection from the dimension A to dimension 7, then it says that that restriction and projection operator first that how to say preserve that actually that that is it looks first you have to say that of course it looks a map from CR solution space to solution space in dimension 7. Of course, you have to say that algebraic curvature also, but the algebraic curvature is only Bianchi identity, so that is very easy to verify. And the second lemma for is take half a page to prove this lemma, not so hard. And then also you have that reduction argument, and you know that's how different is the curvature operator in dimension 7 and the dimension 8. If look only algebra, so that's a dimension 8 and the dimension 7, you know that you have the only solution is a constant curvature, right? So only non-trivial cases, that means what is that part? That part, that means a curvature operator take, I mean that I say in this way, that means that is a value at the SCO as a SCO7 plus 7, right? So that is a answer heuristic to the SO7. You know that it has only a certain solution, so the only asks for that as the condition on the another component. But you have a lot of symmetry because on the equation as a invariant under the spin 7 action, and therefore that is you have the only dimensions R7 to check satisfy some equation, and then you can easily to pick out some conditions. That's not no other solution. Yeah, so that is you can prove the main theorem of the vanishing of the vertical component for torsion tensor. Yeah, so now to prove the main theorem for the second CR condition, we use a Fröhlicher-Nijenhuis bracket. So Fröhlicher-Nijenhuis bracket is the thing that let me recall. That means that you consider the graded Lie algebra of graded derivation of the algebra of differential form on N. So for ADK, that is a tangent value vector form. Then you derive that intersection operator by this intersection and multiplication, and extend it by linear. And then this is a define that is algebraic derivation IK. And now it defines a linear map from the space of tangent value form to the space of derivation of this algebra of exterior form K to K by taking Lie bracket of the algebraic derivation is a natural operator that exterior operator D. And the Fröhlich and the Nijenhuis proved already long time ago that this map is inactive, and the image is exactly that those operator of derivation, that is D and D equal bracket equal 0, and therefore this image is a graded Lie algebra. And now it takes the Fröhlicher-Nijenhuis bracket on this tangent value vector form by this formula. Now, once you know this, then I extend the operator from B to B to the whole the operator on the tangent space by everything outside is equal 0. Yeah. Then we have the following things. The second CR integrability condition is equivalent to the following conditions. That's a projection of the Fröhlicher-Nijenhuis bracket of the I already extended to the whole space by everything answer outside is 0 is equal 0. And then now I said I know that of course it is a tensor because that is a Fröhlicher-Nijenhuis tensor. Now I take that horizontal component of that tensor is I'm sorry, that's of course that's not equal 0 here. I should that is equal PB. Yeah. So if equal 0, if the second condition equal whole naturally is so that's a proposition 2 implies main theorem that is the 6-7. That means that it's a tensor and it's vanished if and only if the second integrability condition hold. So now to see that last thing, that's how to express is in terms of G2 and spin 7 case. So you need to express the horizontal component of the in terms of Levi-Civita connection on the Grassmannian bundle, where G is natural metric. Natural, that means that on the horizontal space it equals on that I'll say on the vertical also, because the vertical is the subspace of the exterior bundle, right? So everything that in case R equal 1, that is Sasaki metric. And you look at the paper by Sasaki, he says that's how to compute Levi-Civita on only the case R equal 1, yes, bundle. He says that after long computation, that's too long, yeah. And then sometimes he writes that's a terrific computation, but unfortunately, fortunately, it doesn't need to compute so much. Yes, so because you have some trick, therefore the computation look quite how to say easy to digest. So now finally I make the in less of 5 minutes. I make the following conclusion and some final remark about the open problem. First, that unite and extend this construction of a CR-twistor space by Leblanc, Rossi, and Verbitsky, respectively, to the case when the underlying Riemannian manifold admits a VCP structure. So it solves the question of the Forman integrability on the CR structure on the twistor space, recovering the resonance by Leblanc and Rossi, respectively, and correcting the resonance by Verbitsky. And we express the Forman integrability of a CR structure in terms of torsion tensor on the underlying space. It connects that the Forman integrability of the CR structure in general case can be expressed in terms of the torsion tensor on the underlying manifold. Yeah, there are possibly several ways to do it. So that's interesting that people never write about it. But the most interesting thing is first that you gave a new characterization of metric of constant curvature on a Riemann manifold of dimension at least 3, lemma 5. Where is the lemma 5? Let me see. Where is the lemma 5? Here. Lemma 5 is that if the element G is connected and equal at least 3 R is a Riemannian curvature, then if the error of the VW belong to the SOAV for any V and V not equal 0, then element G has constant curvature. Yeah, so that is a very simple theorem, but I think that many people know about it, but nobody care to write it explicitly. So and then but the more interesting that how to say that that our theorem form 5, that means for the G2 and spin 7 manifold, you have also the similar characterization of constant curvature. And how to see is in terms of representation theory. That means that given V naught in some two plane, yeah, and R is a algebraic curvature tensor. So let us define a subspace R V naught is some subspace in the SORM. Then we ask us if G is of course G is either SON, G2 and C space acting on R, yeah, and then you have new curvature tensor, and the value at that point still lying in the subspace. So very big constraint. So like a shoe lemma, but it thinks that's some extension of shoe lemma. I try to check a lot of literature, nothing like that. Yeah. So then it's the R constant, and of course the constant curvature is invariant under on any action of the SO G2 and spin 7, and it also has you make the decomposition of the space of the constant curvature tensor, and then in this dimension 7 and 8, there are only one dimensional of the space of the invariant tensor. Either under SO the trivial, G2 also only one dimensional, spin 7 only one dimensional. But you cannot prove by representation theory that the solution is invariant. Yeah. So so some people very strong in representation theory could try to think about this problem. And then, of course, you come to the some hope for study of G2 and spin 7 holonomy manifold using the CR-twistor space. So I finished, and here's our archive paper, and thank you for your attention.
Okay, thanks for the nice talk. Are there any questions? So anyone, any questions from the online audience? So I have a very, very basic question. So
yes.
When you were talking about solving these integrability conditions using the computer, you
yes.
said that you use the computer to check an infinite number of equations. Is that right?
No, that is
so
a thing.
I was a little bit confused.
It was how to say 100 a number. And actually, that's how to say. If you try to write the decomposition of tensor products, that's the biggest space that you need to compute, because it has a multiplicity 2 of the. Not everything is how to say. Then in dimension 54. So that in principle, if you make the decomposition of the tensor product, everything, then you have to make the maximum 54. But then you have to write how to say, maybe the 10 pages of the code here. So you just write a very simple code about less than 4 pages. But then 50 hours of running computer, then you first you try to something 20, 40. No, dimension still too big. Yeah, so it increase. Suddenly it gives a dimension 1 after 100. So that is maybe not so trivial. You don't know, yeah. So that you have to use 100 how to say equation to conclude that that is the system. The system has a dimension not bigger than 1, and because it have only one-dimensional solution, therefore that is the only solution.
The number of equations was finite, just very large, so it makes sense that could be solved with a computer. Okay, so anybody else have some questions?
I have a suggestion about which I am not so sure.
Go ahead, Swatya.
Yes, can you?
Yeah, go ahead, Swatya, please.
Yes.
There are also attempts to cover twistor spaces in Cartan geometry, where there are a bit different notions of curvature and torsion. And torsion is colloquially known to be not determined by the structure. So there are some choices. Andreas Chap, this proponent of Cartan geometry for many years.
So I do not understand your question.
Article, sorry, not so wrote an article 2001, twistor spaces and correspondence spaces, or vice versa. Correspondence spaces and twistor spaces for parabolic geometries. Andreas Chap from Vienna. It is on the archive, where he considered a bit more general situation, but it's a bit different approach. Yes? So, for example, he's not considering Riemannian, but a rather conformal, and then some choices must be done to go back. And he has also here theorems, as I found out, that he has theorems on torsion, regarding torsion in some part of this paper. So all the torsion is important for the integrability problem in several cases, which he calls Grassmannian geometry, which is probably.
So you say that somebody also construct CR-twistor space over Grassmannian?
But it is local, yeah, and it considers only your question, which I felt, which I maybe misleadingly, but I thought that you thought about it as that you can express this integrability via taking the torsion seriously. Yeah? So this is what is also in this approach.
So of course, I mean that I have the several way. I think that I have to say in general case, maybe there are several way to construct this the torsion tensor, because I know that's for the case on more complex structure. Yes, for example, Lichnierovich consider it's a torsion using the connection, and then you consider as a G structure. Yeah, possibly some way, but the one thing how to say the first when we did this, Domenico, it didn't consider the separately is the second condition, and we are very disappointed because we consider first condition is a constant curvature. Then there are almost no how to G2 and spin 7 has a constant curvature. Yeah. So then we say that we have to somehow separate the first and second condition, try to figure out something interesting, and then it's separately. So I think that's of course expressed the torsion tensor curvature for general CR structure possible, but how to decompose it separately so we can get something still interesting for G2 manifold. So, but nevertheless, thank you. Could you send me the email? Is this a reference?
This chap 2001, but I can email it. Yeah? Okay.
A chap. So the chap. I think that sometimes I also follow some paper by chap, but he doing some guys how to say what is a tractor abandon and something like that. It's a paper by chap.
At that time, he wasn't in that time into tractor bundles, as far as I know his story regarding this. But it is connected. Yeah, these are these correspondence spaces. You have a simple Lie group G, then you have two parabolic subgroups, and then you do intersections of these parabolics, and you have projections from G to G over P and from G to G over Q.
Okay, then send me the if you the link, yeah, because it
wouldn't be so maybe so helpful, yeah, because he's computing the projection using some representation theory connected to constant theorem, and he doesn't compute it explicitly, but it might be an inspiration for somebody who is
yeah, sure. I would like to see that how it related. And the second thing that I think that's why that Verbitsky didn't reply to us, because actually it stuck very long time at how to prove that the first condition is the only constant curvature. So because we try to do some representation theory and we spend a lot of time. You see that you have to use 100.
But I think it's a bit more. It's a bit parallel to your approach, yeah. So don't be disappointed if it is really non-usable. This is what you can judge. And I will send it to you, the link.
Yeah, thank you, thank you. Yes.
Okay.
Okay. Any other questions? All right. So it seems no other questions. So let's conclude and thank Van again.
Yes. Thank you. Thank you.